The Steel Framing Industry Association is dedicated to expanding the market for cold-formed steel in construction through programs and initiatives that promote the use of cold-formed steel framing as a sustainable and cost-effective solution, advocate the development and acceptance of favorable code provisions, educate members with reliable data and other critical information that is essential to effective business planning, and create a positive environment for innovation. I'm Larry Williams, SFIA Executive Director. Today's program will be presented by Patrick Ford, a professional engineer who specializes in cold-formed steel framing in structural and non-structural applications. Patrick is also the technical director for SFIA and has been a significant influence on the development of major standards that govern CFS design and construction through committees with AISI and ASTM. So we're in good hands with today's topic, design and hybrid systems for cold-formed steel. Please note that this presentation is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of the presentation without written permission of the SFIA is prohibited. Although the structural frame of a building represents only about 10% of the total construction cost, the choice of material for the frame can have dramatic consequences for subsequent processes. In some cases, the use of multiple materials, called hybrid construction, is desirable because it takes advantage of the unique performance characteristics of each material. This also creates special conditions that the design professional must consider when developing designs for the hybrid system. This program identifies those special situations and provides guidance on how to deal with them. The presentation will cover 4 primary objectives. Participants will have a thorough understanding of the following at the conclusion of the program. Number 1, the circumstances under which a hybrid design might be desirable. Secondly, the basic considerations when evaluating different materials and systems. Also, the design process associated with hybrid structures. And then finally, how to solve common conflicts associated with hybrid structures. I know you'll come away with a great understanding of cold-formed steel. So, Pat, take it away.
Some of you who have heard or seen me before have probably seen that photo. That's a beautiful example of a cold-formed steel structure. And that is a classic Chevelle. And it is actually a composite or hybrid cold-formed steel example. The main structure on that car was cold-formed steel unit body construction, as was the case with many post-1961 American automobiles. In the old days, before the days of advanced automotive engineering, in order to create a convertible, all they did was form the original car, in this case, one of the last years of GM's beautiful A-body muscle car corral, and they would cut the top off. Well, the roof essentially acted like the top flange of a beam on a unit body car, so to cut an entire flange off considerably weakened the structure. In order to regain some strength, they would routinely take hot rolled sections, small hot rolled sections, and weld them into the rocker panels on the sides of the car to help regain some strength. So this is, after fashion, a hybrid cold-formed structure. Now, regarding building structures, hybrid is defined as something heterogeneous in origin or composition or composite. And in the case of building structures, the fact of the matter is that nearly every structure we do is a hybrid to some degree, or at least fits that definition. In this presentation, we're going to look at structures that use large or at least significant portions of the structure to comprise different portions of the overall building. As far as the benefits of doing so, the designer is compelled to take advantage of the inherent positives of each different assembly. It almost goes without saying, because to do otherwise does not necessarily lead you down the road to using a hybrid structure, or at least making that a decision. With regard to cold-formed steel, some of the benefits include non-combustibility, of course. and that is the case with most commercial, industrial, institutional classes of construction assemblies. In the case of cold-formed steel, you also have a very high strength-to-weight ratio and an overall light weight of the assembly. In fact, walls, joists in cold-formed C-shapes could be less or more efficient. Walls, on the other hand, are amongst the most efficient load-carrying elements known to man. In the old days of architectural education, many of you, I know I was included in architectural engineering, were taught in terms of lines and planes. C-stud walls are a plane, a vertical load-carrying plane, and as far as load-carrying capacity to mass, there is virtually nothing, at least that is commonly used, that is as efficient in the world of structural engineering as a cold-formed steel stud wall. It also has relative low cost versus other commercial, industrial, and institutional construction assemblies. For instance, cast-in-place concrete or precast or CMU, etc. There's a potential high speed of construction using prefabrication. And frankly, in the world of cold-formed steel or load-bearing mid-rise cold-formed steel, which is what we're dealing with here, if you are not prefabricating at least the wall framing on that project, frankly, you're not doing it right. And then there's also the relative architectural design freedom of cold-formed steel as a bearing element, in that you can have many irregularities, for instance, in an exterior wall or a bearing wall, whereas to try and do that and articulate an exterior on, for instance, a steel frame, a hot-rolled steel-framed exterior wall, takes quite a bit more work. To do so on a concrete structure does not involve quite as much work, but it involves generally cantilevers between the bays and so on. With cold-formed steel, the wall is simply moved out there, and that becomes the bearing element. Other assemblies obviously have their own strengths as well, including span capabilities, sound qualities, inherent fire ratings, etc. Again, with regard to hybrid structures using cold-formed steel, there are several assemblies that are used with some regularity, at least some regularity, along with cold-formed steel as the primary structural frame. And the ones we'll glance at today, some of them at least, include cold-formed with precast concrete plank or hollow core, long span deck, wood framing, which we actually won't touch on now. You know, the hybrid assemblies that we've dealt with in our office that involve wood framing generally use the cold formed for the strength advantage and the addition of a lower story or stories, and it is almost as if they're sort of cheating the system on the code. So we won't really talk about that very much. Cold formed with bar joists or composite joists, which nowadays can involve either cold formed joists or hot rolled steel bar joists as the composite joists. And then the one that we actually will spend the most time looking at a specific case study with is cold formed with hot rolled steel. This is an example of precast hollow core plank on cold formed steel. It is a 3-story multi-residential building in Michigan. This is a photograph with all the framing in place, and it's topped out, replete with cold formed steel trusses. So the entire assembly, as you can see, is non-combustible. Typically, with precast on cold formed steel studs, and this is becoming a fairly popular option in certain parts of the country. It involves steel stud bearing and exterior wall lines. The primary bracing, or the MWFR bracing, is either provided by cold formed steel shear walls, meaning they are clad, X bracing, which means they're essentially concentrically braced with strap, or reinforced stair and elevator cores. And the main floor spans, of course, are provided by the hollow core plank. The positives on this system are efficiency in moderate to long spans. Precast plank can do a very nice job of spanning great distances at fairly shallow depths, 8 inches and 12 inches. And that span to depth ratio is excellent regarding the precast concrete. The fire and sound rating capabilities are very, very good on precast hollow core plank. The negatives, or at least concerns, include the requirement of soffits or drop ceilings for the MEP in much of the systems throughout the building. It is heavier, if not the heaviest, of all other cold form steel hybrid options. And trade coordination, which is obviously always required on a hybrid assembly, is required especially in this instance with regard to the means and methods of setting the plank on the cold formed walls. My personal preference, for instance, is to have a hot rolled element, or at least a steel tube element, along the top of the wall to avoid damage from impact while the precast concrete is being set. Now, routinely it's done with just a very, very heavy gauge track at the very top, and that would be the very least that I'd expect. But again, personally, I would prefer something very robust at the top of the wall to avoid problems, at least during the actual construction process. Here's a photo of exactly that type of system. You can see the temporary bracing, which ironworkers typically will set precast plank for some reason, and they are not cheap when it comes to providing temporary bracing. And there is also a slight fear factor in this system that they see their very, very heavy elements being placed on these very, very light cold formed stud walls, even though the strength is obviously there. It's been engineered to take the load. And they will not short that building on temporary bracing, which is a good idea because it technically should be there until the building is entirely permanently braced. And you see the weld plates tying the precast plank, every other plank, which is roughly 8 feet on center, to the top of the stud wall. And the way they do that is alternate the embed plates on each plank, and then they checkerboard the plates one side to the other. So the plank that you see here that has no weld plate actually has a weld plate on the other side of the wall, and that helps capture the plank, keep it in place, and also transfer any lateral floor diaphragm shear into the walls as need be. This is an example of a cold formed steel stud and long span deck project. This one we didn't even do ourselves, but they were the best example photographs I could find, so I brought this up. This is an 8-story hotel in Washington State, which is a fairly active seismic zone, or at least this part of it is. And in this type of assembly, you've got steel stud bearing and exterior wall lines. Again, pretty much the same thing. The primary bracing can be done again the same way, either by cold formed steel shear walls, X bracing, or reinforced stair and elevator cores. Excuse me. And one note regarding that, my personal favorite is the last one I just mentioned, which is either reinforced concrete stairs or CMU stairs and elevator cores. And I really believe that's the way to go on any building greater than 5 stories, or at least any cold form primary frame building greater than 5 stories. Below that, X bracing and cold form shear walls are entirely viable, at least if you can have enough of them located in line, and not plus or minus 2 or 3 inches in line, not plus or minus 2 or 3 feet in line, but exactly in line all the way from ground to sky. The beauty of an elevator core is, by necessity, it has to go in line perfectly all the way from ground to sky. And stair cores are usually done the same way as well. But back to this assembly again, the long span deck provides the main floor spans. Now the positives here are a very good span to depth ratio. I would ordinarily call it an excellent span to depth ratio, except for the fact that the long span deck is generally relegated to short to moderate spans, room-sized spans, at least when it's being done reasonably and without massive amounts of reshoring and things that add excessive cost to any given project. It has very good fire and sound rating capabilities. Trade coordination is not a very complex issue in most locales. Some of the issues for concern include the requirement of soffits again, or drop ceilings for MEP, and it is also heavier than most other cold formed steel hybrid options. And as I'd mentioned previously, it's efficient pretty much only in short to moderate spans. Here's a shot of a long span deck on cold formed steel stud project. This is at a lower story of a very tall building, and you'll notice double studs immediately, and a direct alignment with the webs on the long span deck, in this case 12 inches on center. And that's critical in this case for what we call through load transfer. And the through load transfer is relative to the stud load from above, which can become considerable by the time you get to the lower stories. And it has to go through the structural deck and get down to the studs below. Well, generally you want something to be in direct contact. So that's how they solved it on this project. Another alternative would be to have swaged ends, or what they call swaged ends at the deck, which is essentially the high points of the ribs being flattened out or crushed down so that the top of the wall can be cast solid with reinforcing, if need be, as a bond beam. And then you've got automatic direct load transfer, and the bond beam actually can help distribute the loads quite a bit as well, at which point you would not necessarily have to have alignment of studs and deck rib. Here's an example of steel bar joists on cold formed steel, and these are a couple of very, very structurally efficient assemblies, and some of you have heard me say that more than once before too. Bar joists being amongst the most efficient things we know of in the ordinary construction world anyway, for carrying loads horizontally over long spans relative to their own mass. And cold formed steel studs, of course, being very efficient in carrying loads in a vertical plane. This particular project is a 4-story apartment building over retail and parking mixed-use occupancy in the metro Washington, D.C. area. Again, the steel studs provide the bearing and exterior wall lines. The primary bracing is by any of these other methods. Again, my personal preference is to use elevator cores or stair cores once you're above 5 stories or so. And the main floor spans are provided by the steel bar joists. The positives here are the efficiency in long to even very long spans, so apartments, condos, hotels, that sort of thing can very easily span from exterior wall to corridor wall now with an assembly such as this. It's got a good span to depth ratio. You do want to maintain, for instance, an H/20 ratio on the bar joist, just like you would on any routine structural horizontal member. But the benefit of that is within that floor cavity you can contain all the MEP. And this is or can be lighter weight than most, if not all, other cold formed steel or hybrid options. The sound and potentially vibration capabilities are only fair, and we know of vibration issues that are a potential with bar joists in certain applications. And trade coordination becomes a little bit more of an issue with this type of assembly, as well as that through load transfer detail at the bearing line. Load distribution is a separate detail than the through load transfer detail. They both occur at the same location, but it's a separate issue. Load distribution is required when, for instance, the bar joists do not land at the same spacings as the wall studs, which is fairly typical. In fact, it's ordinary. So some element at the top of the wall needs to distribute all that load out, and then you have a through load transfer issue as well, wherein on most bar joist projects, ordinarily the bar joist seat is 2.5 inches deep. It is set on top of whatever the bearing element happens to be. The deck is run all the way through, and then concrete is cast over that. Well, if a stud happens to land in between bar joist seats, it is landing on that deck, and then there's a 2.5 inch airspace directly underneath it, and that load has to be transferred. In the past, some of those details would include a 2.5 inch tube to transfer the force, since the deck could not span between that. Or somehow coming up with a closure detail to slush that entirely solid with concrete. Here's a shot looking down just a short length of that project, and you can see the bar joists holding up ordinary centering and deck, and the evidence of the concrete deck is splattered all over the bottom chords of some of those bar joists. Temporary bracing is in place. The permanent bracing is right here. I don't know if you can see my cursor or not, but it is in place, and that was done routinely, I believe, on this project every other demising wall. So it could be spaced out fairly well on a 4-foot or a 4-story building. As an alternative to this, now, and we have done several projects this way, the deck itself can be used as the primary structural floor, both for diaphragm and for gravity load, and in which case the span of the deck and the spacing of the bar joist has to be reduced somewhat to the point where you can safely carry that load. And the deck, for practical purposes, ends up being required to be a minimum 22 gauge. And then at that point, this can be filled with lightweight gypsum concrete, which has a couple different benefits. It's lighter, number one, so it can reduce all the members all the way down, including foundation reductions, which is always something that should be looked at with any kind of a cold form system because of the weight savings. And cement finishers are not required to finish the work. The Gypcrete guys install it. Supposedly it's self-leveling, although in these cases ordinarily it's very high compression, so it doesn't really level itself out. It has to be screeded off and squeegeed and so on, but it does not require cement finishers, so that the cost is much, much lower. And now let's look at composite joists on cold form steel. And this one we'll look into a little more in depth, and there's a case study that follows this as well. This is comprised of steel stud and or thin-walled hollow shapes at the bearing and exterior wall lines. The primary bracing, again, is provided the very same way, any of the same ways, although, again, in my preference, once above a certain story height, I really, really believe in reinforced stair and elevator cores. And then in this case, the main floor spans are provided by composite joists, either steel bar joists that use a specialized deck or a offset fastener, or nowadays by cold form joists that use one of the same methods, either a composite standoff fastener or an inverted dovetail deck, for instance, to gain the composite strength of the concrete deck. Now, the positives here are that they're very efficient in long spans. There's a very good span to depth ratio, obviously a little bit better than ordinary bar joists. The MEP, again, can be contained within the floor cavity. Routinely, the floor cavities are on the order of a foot or more deep. And special details on some of these proprietary systems are readily addressed by special closure elements that they make. On one of the systems, in fact, the case study system that we're following here, there is a hot rolled member, actually, a channel, miscellaneous channel at the very top of the wall, and what that is designed to do is to distribute the joist loads between the stud or cold form tube members, and do it during construction loads. So it's got to carry the wet load and 20 PSF construction live load during that course of time. And it provides the bottom of the form with these special closures for a solid cast element that goes across the top of that wall, either with or without rebar in place. And that develops a very, very robust distribution element at the top of the wall. When an ordinary deep bar joist seat or a 2.5-inch bar joist seat is used, the distribution of the load amongst the studs, for instance, from bar joists at 4-foot centers to studs at 2-foot or 16-inch centers, is roughly a 95% perfect load distribution. Trade coordination does not seem to be that much of an issue, especially with the thin-walled cold form tube sections, because in this instance they are installed entirely by ironworkers, as is the floor and the deck. Issues to worry about is the sound and vibration capabilities. Again, it's got additional construction issues that have to take up some of those problems. It's heavier than many of the other cold formed or hybrid options, and then it is also slightly more costly, but the idea there being cost savings from time of construction, because this assembly goes up in a very big hurry ordinarily. The case study sample here is Brightview Tenafly. It's senior housing in New Jersey, and in fact this building was only finished, it's not finished yet in fact. It was topped out and the exterior finished and enclosed. It looks finished at this point, but it got to that point pretty much just earlier this month. This is a shot of a crane swinging the panels in place. Each of those verticals happens to be a cold form tube that is smaller than the wall cavity, a hot rolled channel running across the top, a very heavy gauge bottom track, and then some very thin gauge steel studs on the exterior, either 18 or 20 gauge studs, fastened and alongside the tube to help with stiffness and to fur the wall out to pick up the cladding and the interior sheetrock eventually. Here is one of the floor plans for that building, and as you can see, there are plenty of irregularities within that floor plan. Bay windows, bump outs, special headered conditions that cold form studs, or at least some manner of cold form light frame wall, can accommodate very readily. Shear walls in this case, I'm trying to remember if these were diaphragm rated shear walls or if they were X-braced. I think they were X-braced walls, but you can see some of the dark lines running perpendicular to the bearing lines, and those are typically shear walls in this project. Here's a scene of the ironworkers setting an interior panel, and you can see the hot rolled channel on the top and the vertical gauge tubes, which like many things that ironworkers prefer to install, comes unpainted or unfinished, at least ordinarily it does. And the hope there being that the building is enclosed and the moisture in the air and within any construction is normalized in a big hurry, or at least in short order. Again, it's a heavy base track, in this case typically 14 gauge, a top miscellaneous channel to distribute the load and to provide a construction load base for the bar joists, and thin-walled tubes with interior studs typically being 20 gauge. Exterior studs are routinely heavier depending on the finish and the required stiffness. Here is one such top detail. In this case, these vertical tubes are recessed 2 inches from the very front of the wall and 1 inch from the inside of the wall for a couple reasons: to fit the miscellaneous steel channel, number one. Number two, to allow 2 inches of spray-in insulation to go continuously outside the tube. And it's directly up against the steel studs, and it completely fills this cavity on the outside. The bar joist seat in this case, with this particular composite joist system, sits up into the cavity, but they do also use, with some of the systems, saddle seats, which are essentially angles turned the other way, and this becomes a solid pour of concrete within this area. Again, this detail takes care of a lot of sins. The through load transfer issue essentially goes away. Load distribution is enhanced greatly by this detail, and again, it can be done this way or deeper, with an ordinary bar joist seat. Here's a shot of the very same building, and aside from the lack of shear walls, it looks very, very much like an ordinary bar joist on C-stud wall project, and that's what we have here. The only thing you notice are the temporary braces still in place. And there is a photograph of that building, and it's actually a 3 or 4 story plus building in some locations that you can't see, and it does look quite finished. This photograph is from earlier this month, right after the last decent snowfall that hit the East Coast. And at this point, I will pause for any questions. Larry, are there any questions hanging out there for me right now?
I don't see any on the chat screen. If anybody has a question, this would be you want to ask it right now. Raise your hand. Oh, we do have one. I take it back. Nope. I don't have a question.
All right, good. I don't think anybody will complain if we finish early. Part 2 is going to be a single case study, an example of a system that I really, really like, and we've only done this once or twice. I really would like to do more of these. And this, like some of the other projects we were engineer record on, which admittedly helps matters. However, I don't see where there would really be a problem for the engineering design of the cold form being done by somebody providing a deferred submittal on this project for only the cold form steel either. But this system of the building in the background is a cold formed steel on partial steel frame, and you'll see as we get into it pretty much exactly what that means. This is the Courthouse Square condominiums and townhomes in Wheaton, Illinois, which is suburban Chicago. And this case is 6 and 7 stories. The middle segment of this building here is actually 7 stories of load bearing, but the rest of it is precast up to the second level. There's a precast level at the above the basement. There's basement parking, a first floor parking, and then everything above that is cold formed with the steel frame. On this type of structure, we again have steel stud bearing exterior wall lines. We don't have, in this instance, any interior bearing lines. This project uses C-joists for the primary floor, and the main wind force resisting bracing, which is a term that's also used for seismic for some reason, was provided by cold formed steel, a combination of cold formed steel shear walls in this case, and reinforced stair and elevator cores. We did not use the steel rigid frame to resist lateral on this, mainly because we could do it with shear walls in the same instance. Now this is efficient in moderate to long spans, mainly not long to very long spans, as I would say with the bar joist or composite systems, because this uses C-joists. And C-joists, while very strong and lightweight, are not nearly as efficient at their job as C-stud walls are. But you can still get a very good span to depth ratio, and in the instance we had here, we used, I believe, 14-inch C-joists, and the MEP was contained almost entirely within the floor cavity as well. The typical details are common cold form steel construction details. Trade coordination issues were very minimal on this because most of the heavy lifting was done by the carpenters for the cold form steel framing contractor. And this, at least with this structural deck option, is the lightest weight of just about all cold form steel or hybrid options. It has fair sound and fire capabilities, and I say only fair because there are issues where you have to close off with this type of an assembly. You have to close off between common areas and unit areas, things like that. And then the sound capabilities, you know, generally with light frame construction, some sort of resilient channel, sound bats, etc. are required in any case. And then, as is the case, sadly, for many cold form mid-rise construction projects, contractor familiarity is just simply not very strong in many, if not most, locales across the country. Here is one of the main stories. Well, no, it's not. This is the roof framing plan. Although the main stories below are more or less the same as this. This one I can tell because there's a cathedral ceiling frame going on here, and a couple of things that cantilever out that I notice that do not occur otherwise. But you can also notice a lot of irregularity in the exterior bearing line of this C-stud wall. And that is something that you just cannot do very easily with other types of structural assemblies. Here's the foundation, and you can see this is going below grade. The primary steel frame is in place. This is actually a link area to another building that still hasn't been built yet. I think it's going on right now. Sadly, we're not involved in that one. But the link was designed to have terrace loads, so this would be precast, a green area, a parking turnaround, and grass and everything else until you got somewhere in here and a new building would pop up. Over on the left, you see the lower two stories, which is essentially foundation and precast on steel, and you can see the steel column stubs at the interior of the building poking up. Now, what goes on here from here on up is very interesting, and this is a very, very good shot of this. It's an interior steel frame and exterior bearing walls, and then floors are C-joists. And we could have even used a bridge beam and cantilever scheme to lighten up these beams even more, but they were fairly light as it was, and the contractor, as many iron workers do, prefer to go up at least 2 stories with their columns and then just rattle the wide flange beam framing into the sides of those. So that's what we did, and even with that, we were fairly svelte 14-inch beams, which allowed us to have a flush floor system with 14-inch C-joists, and then they spanned from that interior, those 2 interior beam lines, all the way out to the exterior lines. Corridor would be somewhere gerrymandering around in the center bay. And what this did was to create a very, very open floor plan within the body of the building, and this particular tower was condos. So it allowed complete freedom for the breakup of the units and changes and everything else after the fact, which was kind of a key in that market, and this was done. We started at something on the order of 7 years ago. I think it was finished, 5 or 6 years ago at this point. But that's sort of a key, and it also aligned the columns, or allowed the columns to be aligned with the parking grid downstairs, which is very difficult to do. Many of you might know that, is to get a grid that works with various different occupancies. And the key ones to try and work with in our world, in the cold form world, are parking, retail, and apartments. And in this case, we had parking and apartments, and that's exactly what we did. Most of these columns ended up being buried in closets or at wall corners of units and things like that. Here is the joist to beam detail with a couple different options. The ones we actually used are the hanger detail, the cold form steel joist hanger detail on the right, which also involved a continuous strap at the bottom to stabilize the lower flange. And the one on the left actually had steel stud tabs to fasten the track to, or at least that is how it ended up being. And you'll notice a lot of welding. And on the previous slide, if you look at that, you'll notice that there are welders doing the prefab work on the deck, or at least finishing up the prefab work on the deck. And in the old days, welding was considered the way to go on many cold form steel structural projects. If not curtain wall projects, load bearing projects certainly. Here we got higher, and again, the exterior bearing walls allowed for a lot of recesses and projections without any problems for the structure. You can see the steel frame projecting up above, and I think that next level up, the top of those beams, is roof elevation. But the speed with which this went up, which is notable, because it didn't include just the walls, but the C-joists as well. And the C-joists were stick framed, one at a time. And that's advisable most of the time anyway, because of tolerances and things like that. But the construction time was a calendar week to 10 days per story, including beams, joists, everything. And typically the ironworkers would rattle up 2 stories of framing in front of the cold form guys. The carpenters would come in, the steel guys would be out of the way, and their work was not that that heavy, that crane time was an issue or anything like that. And it really went very, very well, at least until the top story. The top story was fairly complicated from an architectural standpoint, so it slowed them down a little bit. But that was the typical rate of construction, a week to 10 days per story. This is the typical exterior bearing detail. Now, it gives a proprietary name on this detail, but it really doesn't matter. It could be any cold form track along the side of the stud walls in a balloon framed type of a situation. And the pre-tab track could be replaced with clip angles. So the C-joists actually come off the side of the wall. The walls are designed for that little bit of eccentricity. And the stud walls are designed to align floor to floor exactly within very, very close tolerances. The C-joists do not necessarily have to align with the studs because the track can distribute that load from stud to stud easily. Typically nowadays they do align, but mainly for the purposes of MEP runs, electrical conduit runs that you want to go between a joist, for instance, not cut through the track and then find that you're landing directly in the middle of the stud. One other point here is that this detail is shown steel to steel for all the connections, including the stud wall to stud wall. But the deck that was used here is a structural cement panel, and there are only 1 or 2 manufacturers of that, so I don't need to use the trade name. But it was tested for crushing capacity and found to be pretty good. In fact, it could go between these stud wall panels and take the full design crushing load nearly all the way down. Not entirely all the way down, but within safety factors the vast majority of the way down. So the deck could be run all the way across and create an interior to exterior platform before the next exterior bearing wall had to be stood up. Here are the cold form steel exterior bearing, of course, occurs at a non-bearing wall, and weatherproofed, at least somewhat dried in. And the sheathing was applied prior to the scaffolding by the masons. One other point here, the brick veneer, which this project ended up being all brick veneer. I think you saw that in the opening slide on this case study. And that brick veneer was designed to go all the way to the foundation, or at least to the cast-in-place wall at the first level. And the requirement for that is that it be engineered brick. The true requirements are nothing earth-shattering. You generally don't have to do anything different whatsoever. Slip ring ties that are specifically designed and called out. Brick strengths that are almost always exceeded by the most mundane brick, and mortar types with prism strengths required of them that again are really no big deal, is all that's required. And drawing call-outs of all those things likewise to show exactly how the brick is to be assembled, and then all loose lintels. And you don't have to relieve the brick dead weight every 30 feet or every story once you're above 30 feet. And that's kind of a big deal. You know, it helps the cold form steel system out itself. The detailing becomes that much easier, and it's allowed to do so because thermally, moisture expansion, everything else, brick and steel framing tend to play fairly nice together. Whereas with some other materials, for instance wood framing, you really couldn't do that. The wood moves quite a bit, you know, from moisture content and thermally for that matter. Now thermally, again, once you're enclosed, it should not change that much, but the brick is not in an enclosed environment, so it is liable to change thermally a little bit. Here's one of the cantilevered balcony framing details. This is another something of an architectural freedom. And these are cantilevered at the very uppermost level. The rest of them were recessed. They created a different architectural feature. Again, another architectural freedom. But the typical balconies at the recesses within the body of the building were done this way, where brackets were welded to the steel studs, and had the loads been any worse, these could have been hot rolled or cold formed tubes, but hollow sections nonetheless. These brackets cantilevered out through the brick. Soft joints would be caulked instead of mortar joints around these brackets, and then the balconies swung in and installed in one piece with railings, deck, and everything else if need be. The very upper level was not prefabbed because of some of these things. The mansard shape was all welded. All these articulated joints were welded, and these members were non-bearing, thank God. Where we did have any sloped members that were bearing, which was not that many, there was actually another straight member, and then we just had to resolve the resultant forces out of it, but we didn't do any with an articulated joint. Where this would typically occur would be at the sides of a large framed opening where we would create a cathedral ceiling or something like that. So these sections of the walls were not bearing. And here are some of those details, as you can see. This is entirely because it's a sidewall. But where it would have been a load-bearing wall, it would have been here, and the load-bearing sections would have been outboard of these particular details. Again, you'll notice all the welded connection details. Here's the upper level cathedral dormers, and again, the cold form steel system allowed for another architectural feature. That's just not that easily achieved with many other systems. And this is a final shot. The building on the right actually is the original Wheaton Courthouse, which was how the project got its name. The building in the foreground left is actually a wood frame townhome type building, and then there were at least planned initially to be several of these buildings, the taller apartment buildings within the grounds. And that's a finished shot of that building. And with that, I will make a summary, and we'll do some final questions and answers, if any. And just to summarize, the hybrid systems can be an excellent solution for complicated or challenging designs, and cold form systems are ideal depending on the use and occupancy. Certain heavier occupancies or heavier load occupancies can lead you in a direction of different systems, of course. The height of the construction, cold form in mid-rise construction can handle story heights of 10 and even more. We have not done more than 10, and you become pressed, especially with a layout that is not very regular, and again without an MWFR system that aligns from ground to sky. And as I had mentioned before, my personal preference for anything over 5 stories is to use reinforced cores, elevator or stair cores. Considerations should be given to the benefits and the downsides, including the strength and weight of cold form steel and costs that are associated with that, primarily in the supporting structure or the foundation. And you should always be looking for those. Larry would also bring up different areas such as insurance and things like that. And I think a lot of those things are going to come to the fore in the near future as well. Integration of other materials, good or bad. Building familiarity is generally a consideration, and a strong one for cold form steel. And then the older I get, the more I think trade coordination is just such a big deal with cold form steel, and with most of these projects that was certainly the case.